Standard unit hydrographs are excellent tools for predicting runoff, provided conditions are perfect. But in the field, we face three recurring problems. A storm's duration doesn't match our existing data, a catchment has zero stream gauge records, or a complex storm drops rain at wildly fluctuating intensities. This flowchart details Sherman's assumptions. Solving these problems requires following the logical progression from uniformity to linear response. These final two constraints are our mathematical levers. Linear response dictates doubling rainfall doubles runoff. Time invariance guarantees delaying rainfall exactly delays runoff without changing its shape. Because natural catchments obey these mathematical constraints, we can confidently manipulate historical hydrograph data to solve complex, real-world hydrological scenarios. This animation illustrates the S-curve. We generate it by mathematically stacking a continuous, infinite succession of standard B-hour unit storms. Eventually, the outflow catches up to the constant rainfall, plateauing at a maximum equilibrium outflow, or QE. To shift our known hydrograph duration from D to a new duration, D', we duplicate the S-curve and lag the entire curve to the right by exactly D' hours. The vertical gap that opens up between these two lines represents our new runoff. Warning tone. But there is a trap here. The gap between these curves represents the runoff for D' hours of rain, which breaks our fundamental 1 centimeter depth rule. We must normalize the output. By multiplying the vertical difference by D over D', we compress or stretch the data back into a standard unit hydrograph. The S-curve operates as a universal time shifter. By building it and shifting it, we can adapt any known historical hydrograph to a completely unrecorded storm duration. For catchments entirely lacking stream gauge data, time-shifting historical records isn't an option. Instead, we extract physical geographic measurements from maps to substitute for the missing flow data. This diagram outlines Snyder's method. We rely on three specific parameters: the total catchment area, the main stream channel length L, and the length from the outlet to a point opposite the basin centroid, known as LCA. These distances give us the standard lag time, TP. However, you must check the storm duration. If your actual design storm duration, TR, does not match the standard duration, TR, you cannot use this output directly. You must calculate the modified lag time, TPR, first. Once the correct modified lag time is secured, we plug it directly into the denominator of the peak discharge formula. This mathematical relationship establishes the absolute peak flow for our synthesized hydrograph. As a brief alternative, the SCS dimensionless unit hydrograph relies on a similar empirical approach, using time of concentration to derive time to peak and peak discharge. Because physical geography dictates water volume and speed, mapping parameters allow us to synthesize reliable flow models without a single drop of historical gauge data. Consider a standard AEE exam scenario. A continuous storm drops 5 centimeters of net rain over 3 hours. The intensity drops, delivering 3 centimeters in the subsequent 3 hours. The river maintains a constant base flow of 10 cubics. We need the total stream flow. Looking at this calculation matrix, we start with our known 3-hour unit hydrograph ordinance. Applying Sherman's linear response rule, we account for the first storm pulse by multiplying the base ordinance by 5. The second storm drops 3 centimeters, so we multiply the original unit hydrograph by 3. But applying time invariance, this rain happened 3 hours later. We visually shift these values down 1 row in our table to precisely align with that 3-hour time delay. Pause the video here, calculate the total direct runoff for hour 6 across the row, and then deduce the final streamflow discharge. Remember the state of the river before the rain started. By breaking a fluctuating storm into isolated, linear components, we can mathematically reconstruct the resulting streamflow. Let's check the hour 6 solution. The scaled ordinate from storm 1 plus the delayed scaled ordinate from storm 2 gives the total direct runoff. But direct runoff is not streamflow. To get the correct streamflow discharge, we must add the constant 10 cubic base flow. Take a screenshot of this. These are the 3 tools we added to the toolkit today: the S-curve for time shifting, Snyder's method for spatial prediction in ungauged basins, and superposition for matrixing real-world storms. Mastering these three transformations bridges the gap between calculating theoretical textbook problems and predicting actual flood events in the field.